This is Physics 2120, Lecture 25, and today we're going to continue to talk about geometric optics. Now Huygens assumed that light is a form of wave motion rather than a stream of particles. And Huygens' principle is a geometric construction for determining the position of a new wave at some point based on the knowledge of the wavefront that preceded it. All points on a given wavefront are taken as point sources for the production of spherical secondary waves called wavelets, which propagate outward through the medium with speeds characteristic of the waves in that medium. After some time has passed, the new position of the wavefront is the surface tangent to the wavelets. So for example, for a plane wave, at t equals 0, the wavefront is indicated by this blue line here. And we just choose some points on there that are going to be sources for these new wavelets. So these wavelets propagate out in spheres, and as they come out in spheres, if I draw a line tangent to all of them, I get my new wavefront. This worked for curved waves too. So here I have my original wavefront. I take some point sources and I propagate circularly out from each of those. And as I do, when I'm done, if I join all them with a line tangent to every wavefront, I get the new wavefront. And so this circular wave expands out as expanding spheres. The law of reflection can be derived from Huygens' principle. So AB is going to be a wavefront of the incident light. So the wave at point A, when it hits, sends out a new wavelet centered at A towards D. And at that same time, B sends out a wavelet centered at B towards C. And I know that the distance from A to D and the distance from B to C are the same, and they're equal to C times however much time difference it took. So, if we look at these triangles, triangle ABC and triangle ADC is congruent to each other. So I know that cosine theta is BC over AC, and cosine theta prime is AD over AC, and since BC and AD are equal to each other, we know that cosine theta is equal to cosine theta prime, therefore theta equals theta prime. So this gives the law of reflection. Theta 1 is equal to theta 1 prime. I can also use Huygens' principle to determine the law of refraction, or Snell's law. So here we have again a wavefront coming down. Now ray 1 strikes the surface at a time interval delta t later. Ray 2 strikes the surface. So delta t is the time it takes the wave here to go from B to C. Now during this time interval, the wave at A sends a new wavelet out centered around A towards D in the new medium. New medium, light is slower, so in this time and this time are the same, but the distances are different because the velocities in the two places are different. So the wave at B sends out a wavelet centered at B towards C. The two wavelets travel in different media, therefore their radii are different. And from triangles ABC and ADC, we see that sine theta 1 is BC over AC, and BC is the velocity in medium 1 divided by AC. And from this triangle, sine theta 2 is AD over AC, where AD is the velocity in medium 2 times delta t. So, we've got these two equations, and we can simplify this by dividing this equation by this equation, and the term AC cancels out. So we have sine theta 1 over sine theta 2 is V1 over V2. But V1 is C over N1, and V2 is C over N2, so this is N2 over N1. So multiplying out, we get N1 sine theta 1 is equal to N2 sine theta 2. This is called Snell's law of refraction. Now, for a given material, the index of refraction typically varies with the wavelength of the light passing through it. So that means the index of refraction depends on the wavelength, and that dependence is called dispersion. So Snell's law indicates that light of different wavelengths are bent at different angles when incident on a refracting material. That index of refraction for the material generally decreases with increasing wavelength. So for example, violet light bends more than red light when passing into a refracting material. The graph here shows how indices of refraction change. So crown glass starts off in the ultraviolet maybe at 1.53, but as it gets towards the red, it can go down to 1.51. And acrylic, infused quartz, and other materials have similar changes. So if I think of light maybe going through a prism, as it comes and it goes through and it's refracted at this surface and refracted at this surface, the angle of deviation is the angle between where the light would go to and where it actually comes out. And that angle of deviation now is going to depend on the wavelength. Since all colors then have different indices of refraction, therefore different angles of deviation, white light, when shined into a prism, spreads out into a spectrum. Blue light spin the most at each surface, so blue light is going to have the bigger angle of deviation than red. In between, we'll have all the different colors of the rainbow. Speaking of a rainbow, let's talk about how that works. So I have a ray of light strikes a drop of water in the atmosphere. And as it does, it's going to undergo both reflection and refraction. First, we're going to have refraction at the front of the drop. Again, violet's going to bend the most, red light is going to deviate the least. So at the back surface, light is reflected. As it is reflected, it returns to the front surface and moves into the air. And the rays leave the drop at various angles. White light comes in, red light gets bent a little bit, reflected off and bent out. Violet's different, and the angular difference on a sphere as light goes through the water, red light is at 42 degrees, violet is at 40 degrees, and all the other colors are going to be between 42 and 40 degrees. So we see a rainbow when the sun is behind us and we're looking at a part of the sky that has water droplets. From the sun, the light comes in white, and as it strikes each droplet of water, we're going to get this effect. It's going to go in all different directions. Well, at the top, the violet light is going to go right over our heads, but in this case, the red light is going to go right to our eyes. And down below, the red light's going to go down towards our feet, but the violet light is going to go towards our eyes. And so as we look out, we're going to see all the different colors in the sky, and this arc, everywhere along this arc, the angle between the white light, or where the sun is, until where the light's coming out, is going to be 40 degrees for violet and 42 degrees for red. Now sometimes you can see a double or even a triple rainbow. And that double rainbow is a lot fainter than the primary. And the secondary rainbow arises from the light that makes two reflections on the interior surface before exiting the rainbow. And higher order rainbows are possible, but their intensities are very low. You have to have very bright sun and very dark background to ever see them. Let's work a problem out with dispersion. A narrow white light beam is incident on a block of fused quartz at an angle of 30 degrees. Find the angular width of the light beam inside the quartz. So, we look at our graph to figure out what the index of refraction is. Blue light, the index of refraction, is about 1.7. And red light is going to be about 1.58. So, 1.470 we'll say at 400 meters, and 1.458 at 700 nanometers. So, using this information, we say index of refraction of air is 1, so sine theta is equal to 1.470 sine theta violet. So solving for theta violet, we get 19.885 degrees. We replete with red, and if we plug all our numbers in for red, we're going to get 20.056 degrees. So our angle of dispersion in there, we subtract the 2, and so we get 0.171 degrees. That's the angular width of the beam inside the quartz. Now there's a phenomenon called total internal reflection that occurs when light is directed from a medium having a given index of refraction towards one having a lower index of refraction. So for example, when moving from water to air or from glass to air. We know that as light comes out, it's bent away from the normal. And so as light comes out at different angles, there's eventually going to come a place where as it hits, when we plug in Snell's law, the light's going to be directed right along the surface. And any more, and it can't go below the surface, and so it's always reflected. So that particular angle of incidence that results in an angle of refraction of 90 degrees is called the critical angle. And sine of the critical angle is equal to n2 over n1, where n2 is less than n1. So for angles of incidence greater than the critical angle, the beam is entirely reflected at the boundary, and it obeys the law of reflection. Total internal reflection occurs only when light is directed from a medium of a given index of refraction towards one of a lower index of refraction. Now one of the applications that we can use for this is fiber optics. A plastic or glass rod is used to pipe light from one place to the other. There's different applications. There's medical use for diagnostic of putting something in that can collect light or can see inside of someone, or telecommunications. Another medical thing is directing lasers inside someone to cut off a piece of cancerous tissue. Lots of different materials that use fiber optics. So the flexible light pipe is called an optical fiber. And the picture here shows a bundle of parallel fibers. In this case, it's an optical transmission line where each fiber then is going to be able to be flashed on and off to get a digital signal. We construct an optical fiber by having a glass or plastic core and then some cladding, and the cladding has to have a lower index of refraction as the core. So that allows light in the core to experience total internal reflection. And typically you put some sort of rubberized jacket around it just to protect it. So let's imagine what a fish looks like, or perhaps you've ever gone to the bottom of a swimming pool, held your breath, and looked up. What's the critical angle for water air? And let's describe what we see when we look up from the bottom of a swimming pool. So first we know sine theta critical is n2 over n1. In this case it's 1 over 1.33 or 0.752. So the critical angle is 48.8 degrees. So then, as we look up, as a fish looks up, anywhere off of this 48-degree angle that they can see out is completely dark. It's mirrored. In fact, we see over here in this picture, looking at this tortoise from the side, that as we look out, it looks like the water looks like a perfect mirror over here. We can't see out of the water because we're not looking up straight enough. Or here's in the ocean looking up. As we look up, we see this ring that we can see out. We can see the sun up there, and we can see the atmosphere. But off to the side here, we can no longer see out. This is why when say a bird is hunting for fish, they're going to come in at a steep angle where the fish can't see the bird until it's too late. Now, Pierre de Fermat developed another principle that can be used to determine the path that light follows as it goes from one place to another. And Fermat's principle states that when a light wave travels between any 2 points, the path it takes is the one that requires the smallest time interval. So the paths of light in a homogeneous medium are always straight lines, because a straight line is always the shortest distance between 2 points. But using a little bit of geometry, we can use Fermat's principle to derive Snell's law of refraction and the law of reflection. For the next exam, you should know how to derive Snell's law either using Huygens' principle, as I showed you, or Fermat's principle, which is available in your book, or you could find it online. So to review what we talked about today, we talked about Huygens' principle and how we can generate a new wavefront by imagining small wavelets coming off of an old wavefront. We talked about dispersion, that light of different wavelengths travel at different speeds in materials. We talked about total internal reflection, how there's a critical angle as light is going from a high to a low index of refraction, that all light is reflected. And last, we ended up with Fermat's principle, which says light always follows the path that's going to take the least amount of time.